Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss fixed bias. Let's begin. We have already discussed regarding DC load line and Q point. On that basis, by using the concept of Q point, we can easily say either that a transistor is properly biased or not. If that Q point or what we call as operating point is fixed, then that transistor is said to be proper biased, means it is functional. If any fluctuation occurred in that of Q point, then we say that transistor is not proper biased and the functionality of transistor not holds good. So, there are various types of biasing to fix that Q point. One of the biasing method is fixed bias method. In that particular video, we have analyzing what is fixed bias method. Let me consider an NPN transistor with common emitter configuration. Here a resistor having resistance, let RC, another resistor having resistance RB, DC potential plus VCC. That is the emitter, that one is the base, this one is the collector, that end is earthed. The base current, is the collector current and emitter current. That VCC is not the potential difference, that is a point potential. That end is positive, this end is positive. Now, that configuration, we can change that configuration as simplified. This is NPN transistor. That end is positive, that is earthed, higher potential, lower potential. We can say that is positive end, this one is the negative end, and the potential difference, the potential to that of emitter base junction VEB, emitter base potential. In that of end collector and emitter, the potential common emitter, that end is positive, this end is negative. this end is connected to positive, that end is connected to negative. Okay, that is VCC. Similarly, that end also positive, this end as negative. Here is the resistor having the resistance RC and the current, collector current IC. This end is connected to the positive end, that end is connected to that negative end. Positive, negative, VCC, VCC. Emitter current IE. Now that configuration is totally changed to this configuration in a simplified manner. We can apply Kirchhoff's voltage law in input, that input is the emitter base junction. Here it will be the potential VEB, output at the collector emitter junction, collector emitter junction VC. In that of DC load line, look here, if I plot a DC load line, DC load line, that is the output characteristic in between VCE and IC at a constant IB, at a constant IB. DC load line AB, which cut that IB at a point which is the Q point or operating point. So the coordinate of that Q point is VCE IC. The value of VCE and IC decide what will be the exact point, that Q, which one is operating point or Q point. If that is fixed, then the transistor is said to be proper biased. If that is not, then we call the transistor is not proper biased. Now to fix that Q point, we have to know the value of IC, VC and IB, and that value can be easily calculated by using that kind of configuration. And here we apply KVL, Kirchhoff's voltage law in input junction as well as output junction. Applying Kirchhoff's voltage law in input junction, we have Kirchhoff's voltage law is applied in that of input junction. Here is plus VCC potential drop, IB RB minus IB RB minus VEB is equal to 0, or VCC is equal to IB RB plus VEB, or IB RB is equal to VCC minus VEB, or IB is equal to VCC minus VEB divided by RB. Look here, the potential of output junction is more as comparison to that of input junction, and that difference is too huge. That's why we neglect the lower potential. As VEB much more less than that of VCC, then it is neglected. Therefore, base current IB is equal to that VEB is neglected, so it is VCC divided by IB, VCC divided by RB. Equation number 1. We know that the collector current IC is equal to beta times of IB plus some factor related to leakage current. Here we neglect the leakage current sector, as that leakage current is too less, so we can neglect it. Now the value of IB can be put here. Therefore, IC is equal to beta times, beta is the amplification factor, value of IB as VCC divided by RB. It is the value of IB. Next, we can apply KVL on that of output junction. Now, applying Kirchhoff's voltage law in output junction, we obtain VCC potential drop ICRC minus ICRC. Next, potential VCE is equal to 0, or VCC is equal to ICRC plus VCE, or VCE is equal to VCC minus ICRC, or VCE is equal to VCC minus the value of IC as beta VCC divided by RB into RC. The equation number 3, that is equation number 2, equation number 1. Look the 3 equations. IB is equal to VCC by RB. The value of VCC known to us, RB, that is a resistor we use, and that value also known to us. Then IB is calculated. As IB is fixed, then IC also fixed. Amplification factor we known, IC is fixed, then all such values in that of VCE also fixed. From the above equations, it is confirmed that the value of IB, IC and VCE are fixed. That's the reason as we say the type of biasing as fixed biased. In this way, the coordinate Q as VC, IC and IB is fixed, and the transistor now proper biased by fixing that operating point Q. That method of biasing is known as fixed bias. That method has its own advantages as well as disadvantages. Let me show what be the advantages. Advantage in that advantage section, as we use the resistors, so it is very simple because we use the high resistance as far as our necessity is concerned. It is simple to use high resistance is necessary. Next advantage, the calculations are very simple. The calculations are very simple to set that biasing. To set that biasing, our requirement is IB, IC and VCE. Since it is the high resistance as our requirement, so the calculation is very easy to us. Next, some disadvantages. Of that biasing. It provides poor stabilization. Poor stabilization. How? Because there is no means to stop the increase in collector current, due to increase in temperature and variation in transistor parameter. Transistor parameter, we have already known how these factors influence the fluctuation in that of Q point, that is variation in temperature as well as variation in transistor parameter. And again, it has poor thermal stability for that of large extent. Again, it has poor thermal stability due to large value of stability factor. That the advantage, sorry, that is the disadvantage for that fixed bias transistor method. So with the help of this video lecture, we understand the concept of fixed bias transistor method, that is the circuit, how that circuit configuration changed, and we apply KVL both input as well as output junction, and its advantages as well as disadvantages. So with this useful and informative notes, let me wind up this session. Thank you.